Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 39 of the Statistical Thermodynamics for Engineers course. So we just now saw that, we write it once again, that Z is equal to C I is also equal to C double integral exponential minus H KT dP. Okay, so in this particular case, as we saw, it is highly, this equation is highly significant because it relates the partition function to the phase integral. So partition function is basically quantum mechanics. Phase integral is classical mechanics. So this is classical mechanics. Partition function is quantum mechanics. Okay. So definitely, more importantly, okay, definite point, by the definite point in the phase space is permitted by classical mechanics. The same is not true for quantum mechanics due to uncertainty principle. On this basis, the value of C establishes a statistical mechanical equivalent of the correspondence principle. Okay, so C, this constant C over here, this guy, this can be interpreted as the number. C can be interpreted okay, as the number of quantum states, okay, per area in phase space. Okay, per area in phase space. So this is the interpretation of C. As a result, inverse of C inverse, okay, C inverse, it must be the area in phase space, okay, corresponding to one single quantum state. Okay, one single quantum state. So we can now evaluate C, and now evaluate C by introducing a phase space representation of classic harmonic classic harmonic oscillator. Okay. So if you look at this, if you look at this expression once again, which is a Hamiltonian, okay, not square. If you look at this once again, rewrite this. Okay, so from here, curves of constant vibrational energy in phase space, okay, and expressed as, okay, so the curves of constant vibrational energy in the phase space can be expressed as square plus square r square Beta square is equal to 1. And the square is equal to 2 mu beta square is equal to 8. Okay. These are curves. These are curves of constant vibrational energy in the phase space. It's expressed like this. Okay. Constant vibrational energy. Okay. So for an harmonic oscillator, therefore, for an harmonic oscillator, we find that all combinations of momentum and position combination giving the same total energy. We define an ellipse in phase space. Phase space. So the area circumscribed by this ellipse, the area circumscribed by this ellipse is A alpha beta to 2 pi energy by A naught. Yes. Okay. So this is expressed in terms of the fundamental. This is the fundamental vibrational frequency. Fundamental vibrational frequency. Okay. Okay. Because the inverse of C is the area in the phase space corresponding to one quantum state, we may evaluate C by determining the differences in phase space area for two successive vibrational quantum numbers, right? Okay. So since inverse of C, okay, is the area in phase space, okay, corresponding to one single quantum state. Okay, we may evaluate C. We may evaluate C by determining okay, the difference in phase space area okay, for two successive vibrational quantum numbers. Okay, two successive vibrational quantum numbers. This incremental area identifies a single quantum state. This incremental area okay, identifies a single quantum state for harmonic oscillator. Okay. So if you look at this now, draw this. This is how. Okay, so go around this. Then okay, so E constant. So this is V. Let's say V plus 1. And this area representing a single quantum state or harmonic oscillator. Or harmonic oscillator. So this equation is highly significant, as we already saw over there. Okay. So now using this figure, okay, now what we can do, we can find out the two areas, area V plus 1 minus area AV, which is basically equal to now AV, which is equal to H. So we find that this is the Planck's constant. The Planck's constant can be uniquely interpreted as the area in phase space, okay, corresponding to a single quantum state. Okay. So by utilizing the phase space representation, okay, as portrayed by the figure, okay, we have shown C is equal to therefore H inverse. Given the magnitude of the Planck's constant, okay, so the number of quantum states, so therefore this implies number of quantum states per area of phase space is gigantic. It's enormous. Okay? Therefore, the partition function, remember we wrote it as C, so now this becomes 1 over H integral E minus HPR by KT dP for a single DOF. Okay? So for n degrees of freedom, okay, the partition function can be related to the phase integral as HA. Phase integral itself is written as right. Okay. For a Cartesian coordinate having, say, 3 degrees of freedom. Okay. So this becomes for 3 DOF So HPR has been cast in terms of generalized momentum and position vectors, PR, thus indicating a potential dependence on all three momentum and position coordinates. So you can see that for n degrees of freedom, this is what is valid, and this is a sample phase integral. For 3 degrees of freedom, it's a little bit more complicated than that. And we also saw the association, very clear association between C and the number of quantum states and basically H, the Planck's constant. And the Planck's constant was uniquely interpreted as the area in the phase space corresponding to a single quantum state. Okay. So this sets the stage. Now that we know all these things are now well done, we have defined the phase integral. We are now prepared to evaluate the contributions of U and CV from translational, rotational, and vibrational energy levels. Okay. So U and CV. Okay. The electronic mode cannot be considered as an input, always requires the application of quantum mechanics. In general, the contribution from each of the classical energy mode is prescribed by the equipartition principle. So let's write what is the equipartition principle. Okay, so equipartition principle, each independent pure quadratic momentum or position term in the classical energy of a particle contributes as RT by 2, R2 to the thermodynamic internal energy, heat capacity per mole. So each independent pure quadratic momentum of position or in classical energy of a particle contributes RT by 2 to the thermodynamic internal energy or heat capacity. So that is R by 2 for heat capacity, basically heat capacity per To prove this principle, we again make use of the harmonic oscillator. For this case, we show that the pure quadratic momentum term is p squared by 2 mu, where the pure quadratic position term is k naught r squared by 2. Okay, so pure quadratic momentum term is squared by 2 mu, where the pure quadratic position term is a naught r squared by 2. Okay, so if we make use of this is all making use of the harmonic oscillator. To prove this principle, that is what we have done. Okay, now for a result for a simple degree, you can see the math. There's a little bit of math involved, so you can check that out. And I'm just going to write the result for a single GOF is z equal to 1 over h minus infinity plus infinity exponential minus p squared by 2 mu kt k naught squared 2 kt also equal to 1 over h to 2 pi mu kt multiplied by 2 kt by k naught So we have conveniently done what? We have separated the contributions to the partition function from the independent momentum and position terms. Okay? We have successfully conveniently separated contributions from independent momentum and position terms. Okay. So we have separated their contributions to the partition function. Okay. On this basis, the universal contribution to the partition function in either case is given by universal contribution okay, to the partition function. Is Z. Okay. So the allocation, okay, to internal energy from either pure quadratic term is, for example, U by RT is T Z by B is equal to half. Okay. Similarly, CV by R equal to CV by R is equal to also equal to half. Therefore, at thermodynamic equilibrium, okay, we have shown that any pure quadratic term contributes RT by 2 to U and per mole, and R by 2 to heat capacity per mole. This conclusion is clearly unaffected whether the pure quadratic term is based on momentum or position. So this validates what we call the classical equipartition principle. Okay, so if we just write this thing with the contribution, translation, rotation, iteration as a total. Okay, this. Okay, so the contribution is classical. Okay, you have 1 over 2m x squared is y squared plus z squared. Okay, degrees of freedom is 3. Internal energy U is 3 by 2 RT, and heat capacity is CV equal to 3 by 2 R. The rotation contribution is 1 over 2I squared L Z squared. It's 2, so we already know RT. And the vibrational contribution is x squared by 2 mu plus a naught x squared by 2. So 1 RT R. The total contribution would be, this is 6 7 by 2 RT. So 7 by 2 R. Okay. This is for a diatomic molecule. Okay, so now of course you can calculate once you know all these things in details. Now you can calculate, invoke the equipartition principle, and we can determine internal energy and heat capacity for a classic diatomic molecule, which is what we summarized just now. The translational mode is purely 3 pure quadratic momentum terms, one for each translational mode of freedom. Rotation has 2 degrees of freedom corresponding to two pure quadratic momentum terms. In comparison, the vibration possesses a single degree of freedom, but two independent quadratic terms, one based on momentum and the other based on position. The additional quadratic term for vibration arises from its potential energy, which is missing from its translational and rotational modes. We'll cover more of this in the next class when we look at these principles. That we use this to calculate the effect of temperature on, say, the specific heat of a particular molecule. And then once it is done, then we can of course calculate all the other properties that are there, right? H and CV and enthalpy and all those other things, okay, in the subsequent class. Thank you for listening.